time. It's the invisible scaffold of our lives.
It really is.
And it feels so simple, so intuitive, until you actually have to stop and, explain it.
Right.
We all say things like tomorrow or 3 hours ago or last winter without even thinking. It just flows. But imagine for a second you're a machine.
A computer program.
Yeah, just logic gates and code trying to understand human language. All of a sudden, those simple words are not simple at all. They're just, a total minefield.
And that's really the ultimate paradox
Mhm.
of natural language processing. I mean, as humans, we see time as this obvious linear river that just flows one way.
We're born, we live, we move forward.
But linguistically,
Yeah.
oh, it's a mess. It is just a tangle of context and implied meanings, cultural stuff, hidden rules, and that's exactly what we're unpacking today.
We're looking at a really fascinating text. It's called Temporal Processing, Interpreting and Ordering Time in Language by Inderjeet Mani.
Yeah, this chapter is,
Yeah,
it's a big way.
It is, and the mission here is huge. We're not just trying to get a computer to read a date off a calendar, like, scanning a document for July 4th.
That's the easy part.
That's the easy part. We are trying to teach a machine the flow of time, the chronology, the duration, cause and effect.
And that's the critical distinction. I mean, think about the phrase, I'll do it later.
Okay.
As a person, you just know what that means from context. If I'm washing dishes, later is probably 10 minutes. If I'm talking about writing my memoirs, later could be 20 years.
But a computer hates that. It hates ambiguity. It wants a timestamp.
It demands one. A computer needs to map later to like a specific mathematical value on a timeline. And this isn't just some, philosophical exercise.
Well, it has real-world stakes.
Big time. This is the backbone of automatic news summarization. Those advanced question answering systems like Siri or Alexa, even weather modeling.
Right, because if an AI can't order events, it can't understand a story. It's just looking at a bag of words.
Exactly. If a system doesn't know the heavy rain happened before the flood, it hasn't understood the news report. It just recognized two key words, rain and flood. The causality, the whole story, is gone.
So, okay, let's get into the mechanics here. The source kicks things off by laying out the toolkit that we humans use to talk about time, and it seems like we have three main tools.
We do. The first one is the most obvious one and the easiest for computers. Time and date locutions.
So, explicit references.
Your clocks and your calendars. 3 o'clock, tomorrow afternoon, 3 days a year. The stuff you'd write in a planner.
Okay, got it. Then what's next?
Then you have tense. This basically positions an event relative to right now, the moment you're speaking, past, present, future.
I ate, I am eating, I will eat. Simple.
Simple enough. But then there's the third one, and this is where people, and definitely machines, get tripped up, and that's aspect.
Aspect. Okay, I admit, this one always confuses me a little. How is it different from tense?
So think of tense as where the event is on the timeline. Aspect is more like the internal shape of the event. Is it finished, or is it still going on?
Give me an example.
Okay, compare we drove to we were driving.
Okay. We drove sounds like the trip's over. Done. We were driving sounds like I'm in the middle of a story about something that happened during the trip.
Precisely. Both are past tense, but we drove sees the event as a closed, completed thing. We were driving puts you, the listener, right in the middle of the action. That distinction is, crucial for a computer trying to figure out if something is over.
Okay, so tense, aspect, and locutions. If it was just those three things, it feels like you could build a decent rule-based system.
You'd think so.
Find the verb, find the date, boom, timeline. But this is where the source just throws a massive wrench in the whole thing. This system is not universal.
Not even close. And that is the absolute nightmare for anyone trying to design a global AI. We tend to assume that because time is a law of physics, the way we talk about it must be a law of language.
But it's not.
It's not. You can't just code English grammar rules and expect it to work for the whole world. The source has some incredible examples of this cross-linguistic chaos.
The one that blew my mind was Chibemba. It's a Bantu language spoken in Zambia.
Chibemba. It's a linguist's dream and a programmer's headache.
Right. So in English, we're basically happy with past or not past.
But Chibemba slices time so much thinner. It has 4 distinct past tenses and 4 distinct future tenses.
4 past tenses, so you can't just say, I went.
Nope. You have to specify how far back went was. There's a tense just for earlier today, a different one for yesterday, another for within the last few days, and a fourth one for the distant past.
Wow. So if you're building a translation AI and it sees the English sentence, I went to the store, it's stuck.
It's completely stuck. The English sentence just doesn't have enough data. The machine has to guess the temporal distance from context, and that's where you get errors.
And then you swing to the complete opposite end of the spectrum with, say, Mandarin Chinese.
Correct. Mandarin doesn't really have grammaticalized tense. You don't change the verb from walk to walked.
Oh, how does it work?
You rely on context, aspect markers, and time words. So if you say, I go to store yesterday, the word yesterday is doing all the heavy lifting. The verb itself stays neutral.
And then there's Burmese, which the source calls even more impoverished untense. It doesn't really do past, present, or future at all. It uses particles for something called realis versus irrealis.
This is one of my favorite concepts. It sounds so philosophical because it kind of is.
Realis and irrealis.
It's a totally different way of seeing reality. Realis covers things that have actually happened or are happening facts. Irrealis is for things that are potential, imagined, or in the future.
So the main distinction isn't when did it happen, it's is this a real fact or just an idea?
Exactly. I ate is realis. It's a fact. I will eat is irrealis. It's a projection. So if you're an AI trying to build a timeline and the language you're parsing doesn't care about when, only about if, you have to just rebuild your whole architecture.
The big takeaway here is that a temporal processing system has to be, as the source says, cognizant of all these different features. You can't just build one time machine that only speaks English.
You absolutely cannot.
Okay, so the linguistic landscape is messy. Let's talk about how the engineers try to solve this. The first step, the source says, is just spotting the time expressions, information extraction.
Right. Before you can order events, you got to find the timestamps. And in the field, they use an annotation scheme called timex2.
Timex2, it sounds like a watch brand from the 80s.
It does. But it's a set of tags, a standard for categorizing time expressions. And the big distinction it makes is between points and durations.
Okay, break that down for me.
A point is a specific spot on the calendar. Today, July 15th, 1999, a duration is a quantity, a length of time, 3 hours, 2 weeks.
So if the text says he wrapped up a 3-hour meeting, the system tags 3 hour as a duration.
Correct. And if it also says today, then today gets a calendar value based on when the document was published. But here's the problem. We humans are vague. We say things like, it was an unusually mild winter.
And winter isn't a single date. It's a season. It shifts.
It has fuzzy boundaries.
Yeah.
But the machine has to tag it. So timex2 has a code for it, XXXWI. It means the winter of whatever the reference year is. It's a structured code for a vague human concept.
But sometimes it's not just vague, it's genuinely ambiguous. The source has this perfect example about a sheep shearer from New Zealand.
Ah, the Rodney Sutton example. Yes, this is a classic edge case that just breaks all the simple rules.
Okay, so the news report says 16 years of experience and 10 months of training are paying off for a sheep shearer. Rodney Sutton broke a record.
Okay, so the machine scans that. It sees 10 months of training. That's easy. That's a duration tag. But to put it on a timeline, it needs to know when that training ended.
Well, as a human, I just assume it ended right before he broke the record. I mean, why else would you mention it?
That's the common sense assumption, yes. But does the text explicitly say that? Did the training end the day before, a week before? Did it overlap with his 16 years of experience?
I see the problem. The text implies it, but it doesn't state it.
And because it's open to interpretation, even human experts can't agree. The source says inter-annotator agreement on this stuff is only around 80 to 85%.
Which means almost 1 out of 5 times we can't even agree among ourselves what the timeline is.
And if we can't agree, what ground truth does the machine learn from? So this is where they develop hybrid systems.
A mix of rules and machine learning.
Exactly. It uses something called a direction classifier to look at the verb tense and figure out, is this time before or after the reference time? And then temporal anchoring connects a word like Thursday to a specific date based on the document's timestamp.
So if the article is dated Friday the 14th and it says last Thursday, the machine does the math and anchors it to the 6th.
Exactly. And honestly, that part, spotting the expressions, we're getting pretty good at that. Success rates are upwards of 90%.
But finding the dates is the easy part.
Finding the dates is the easy part. The hard part is figuring out the story, ordering the events in a narrative. That's the real frontier.
Because stories aren't always chronological. We use flashbacks, we explain things out of order.
Right. There's a narrative convention where we usually list things as they happen. Max stood up. John greeted him.
Stand up, then greet. Easy.
But we break that rule all the time. The source gives this great example. Yesterday, Max fell and broke his leg. John pushed him.
Ah, and suddenly the timeline has to loop back on itself? John pushed him before he fell, but the sentence about the push comes last.
Because it's an explanation, what we call a discourse relation. A smart system has to realize that, despite the word order, the pushing event happened before the falling event. And that relies on world knowledge causes have to precede effects.
So to map this mathematically, the source brings up Allen's interval calculus. This felt like the heavy math part of the chapter.
It is. This is the gold standard from James Allen back in 1983. He said we need to think about time in intervals, or chunks, not just points. And he defined 13 possible relations between any two intervals.
13. I can think of like before, after, during. What else is there?
It gets very, very precise. You have A starts B, A finishes B, A overlaps B. My favorite is A meets B.
What's A meets B?
It means interval A ends at the exact nanosecond that interval B begins, like a baton pass in a relay race. No gap, no overlap.
Okay, I see. So before would imply there's a gap between them. Meets means they touch.
Yeah, exactly. And Allen's 13 relations cover every possible physical interaction. So the computer tries to build a giant web where every event is a node, and the lines connecting them are these rules.
But here's the catch you mentioned. Humans are terrible at annotating this. The inter-annotator agreement is only about 55%.
55%. It's barely better than a coin flip. And it's because reality is messy. The source uses the gloves example to explain why. It's from a text about the O.J. Simpson trial.
Right. The text says, Shapiro said he tried on the gloves and realized they would never fit.
Okay, two events. Tried on and realized. Put them on a timeline. Did he realize they wouldn't fit after he finished trying them on? Or did the realization happen during the act of trying them on?
I mean, probably during.
Right.
As he was pulling at them.
Probably. But you can't be sure. Maybe he took them off, looked at his hands, and then it hit him. The text is ambiguous. It's what we call a disjunction. It could be A or B.
And computer systems hate maybe.
They despise it. They want one clear answer. And because we humans can't agree on the nuances that during or after, the training data is messy. You feed a messy data set to a model, you get a messy model.
So we have a system that needs this precise math from Allen's 13 rules, but it's being fed inherently fuzzy data. How do you even begin to solve that?
You turn to logic. This brings us to temporal closure and common sense.
Temporal closure sounds like a sci-fi movie title.
It's basically a sanity check. It uses the transitive property. If A is before B and B is before C, the machine absolutely must infer that A is before C.
That seems incredibly obvious. Why do you need a special algorithm for that?
Because a machine learning model often looks at pairs of events in isolation. It might say A is before B with 80% confidence, and B is before C with 80% confidence. But then it looks at A and C separately, gets confused, and says C is before A.
And it creates a time loop, a paradox.
Exactly, an impossible timeline. So researchers use something called integer linear programming, or ILP.
This was the really technical part of the source. How does ILP fix the paradox?
Think of it like a Sudoku puzzle. You can't just fill in one square without checking the whole row, the column, and the box. ILP is a global optimization technique. It forces the system to look at the entire timeline at once and mathematically make sure there are no contradictions. It enforces sanity.
It stops the AI from hallucinating a time machine.
Basically. But logic only gets you so far. You still need common sense, especially about how long things take.
The duration intuition.
Yeah. A computer has zero life experience.
Yeah.
It doesn't know that watching a movie usually takes a couple of hours, while a plane taking off takes, 30 seconds? To a computer, they're just events.
There was that study mentioned, Pan et al., from 2006.
Yes, they tried to teach computers this intuition. They annotated a huge text corpus with minimum and maximum durations for different events. They were trying to teach it probability. Like, if the text says ate dinner, it probably lasted between 30 minutes and 2 hours.
And how'd the machine do?
It was okay.
Yeah.
About 76% accuracy in guessing if an event lasted longer than a day. But that still means a quarter of the time the machine has no clue if dinner takes an hour or a week.
Which is a pretty big margin of error if you're trying to understand, say, a crime timeline or a medical history.
Absolutely. Which brings us to the so what part. Why does any of this matter? And the source points to two huge applications: question answering and storytelling.
Question answering, QA, that seems to be the holy grail right now. We want to ask computers complex questions like we'd ask a person.
And to do that, the computer needs to do what they call temporal algebra. The example in the source is great. Where did Bill Clinton study before going to Oxford?
A human knows that instantly. Georgetown.
But look at what the machine has to do. It can't just match keywords. If it searches Clinton and study, it gets a list. Georgetown, Oxford, and Yale.
Okay, so it has the list.
Right. Then it has to extract the dates. Oxford was 1968, Georgetown was 64 to 68, Yale was 70 to 73.
And then it has to process the word before in my question.
That's the operator. He uses that temporal signal before to filter the list. Yale is after 1968, so throw it out. Georgetown is before 1968. Keep it. The answer is Georgetown.
It really is like algebra with historical facts.
It is, but it requires the system to get the timeline perfectly right. If it messes up the dates or misunderstands before, the whole answer collapses.
And the other big application is natural language generation. AI writing stories.
Yeah, systems like Storybook, this is where the machine is the narrator. It takes a bunch of facts and it has to plan a coherent narrative.
And the source used Little Red Riding Hood as an example.
A classic. And what's really impressive is how the system handles the tense shifting between the story's narration and the dialogue.
Oh, that's something you don't even think about. The story is told in the past tense. Little Red Riding Hood walked through the woods.
But then she speaks in the present tense. Where are you going? The system has to know to switch. And then it has to immediately snap back to past tense for the narrator tag. Little Red Riding Hood replied,
I am going to my grandmother's house.
Exactly. It seems trivial to us, but for an algorithm to manage those different layers of time, the story's timeline versus the speech's timeline, it's a really complex planning task. It's like it has to keep two clocks running in its head at the same time.
So to bring this all together, we've gone from the chaos of Burmese particles to the sheep shearer's vague training schedule, O.J. Simpson's gloves, and all the way to Bill Clinton's college history.
It's been quite a journey through the mechanics of reality.
So where are we now? If you had to give AI a report card on understanding time,
I'd say for identifying the time expressions, spotting the dates, the points, we're doing really well. A+ work. 90% accuracy or better? That problem is, mostly solved.
ordering the events.
That's where we're struggling. Understanding the story. That 55–60% accuracy on the time ML links tells you everything. We have a long, long way to go.
And the source says we need more data, as always.
Always more data. But more than that, it argues for temporal reasoning. We can't just rely on pattern matching from huge neural networks. We need algorithms that actually understand the logic of time.
It's the difference between memorizing a history book and actually understanding cause and effect.
That's the perfect analogy. We need machines that can reason, not just retrieve.
Something struck me reading this. The source mentions that different applications need different kinds of time processing. A biography's timeline is different from a news summary's timeline.
Yeah, the granularity changes. A news summary might care about minutes. A biography cares about decades.
So here's my question for you and for everyone listening. If machines perceive time differently based on their programming, if one AI sees time as a precise sequence of timestamps and another sees it as a fuzzy cloud of probabilities, will AI eventually develop a concept of history that is just fundamentally alien to how we experience it?
That is a profound question. We experience time as a river, right? It flows one way, we're carried along, we can't go back. But an AI, with a perfect database, experiences all of time simultaneously. It can access 1999 and 2024 with the same speed, the same clarity. To an AI, history isn't a river, it's a map. It's a landscape it can fly over in any direction, looking at the patterns from above.
In the map of time, I really like that image. It changes how you think about the mind of the machine. Something to think about the next time you tell your phone to set an alarm for later.
Thanks for listening to this deep dive into temporal processing.
It was a pleasure.
See you next time.